Cool, you're on our way. Thank you everyone for turning up to this talk. My name is Afif Mohammed. I am an independent consultant for the last four years now. Currently I'm consulting at Seek in the engineering stream. Prior to that I was at a logistics company called IBSA, where they were building platforms as a service and whatnot for e-commerce. And before then, I was at Scoopon. Responsibilities primarily where you walk into a space where the application kind of has hit a plateau, and they really want to refactor and move it to microservices for lack of a better word, so they can really scale and accommodate and bring in all the good growth that they're after. At Scoopon, I was fortunate enough to have that opportunity to really be able to take the whole application, refactor it, make it completely distributed. Got a lot of learnings from that. That was on AWS, and then moved to IBSA. Fortunate enough to land a similar opportunity. This time went into Azure with microservices, and got some learnings out of that. And then now at Seek. My talk today is, so really when we approach these sort of problems, it's all about what is the mindset and what problems are you looking to solve at the outset, and how do you want to approach, what characteristics are you looking for, and where do you almost go achievement unlock. Yes, I've done that. That's what I set out to do. From my experience, what I've done in the last 3-4 years, I have developed obviously an understanding of how I would like to approach these things, and how I, in my head, think that is what prepares you best to succeed, and it aligns you with how microservices function. So I'm hoping to give some of that in today's talk. So I tried. Originally, the intention was to make it more concrete. That's just relax. Yeah, the intention originally was to make it more concrete, but then I realized there's so much that goes into it with the approach that I'm taking. I really wanted to take it a step back and talk more about the mindset and the design and how I really approach these problems when I enter a monolith, and where do I build it to. So these are the talk outcomes. I'm really looking as an outcome that when I'm done with this talk, you probably have an understanding as to what you should approach first to succeed best with microservices, and really what is microservices trying to solve? Why did it come about, and what does it do that wasn't done before? So one of the main things that's very unanimous with microservices is Unix programs. It's very clearly coded that they take a lot of inspiration from Unix, hence it's not something new. It goes back all the way to Unix. And what they're referring to is this rich composability that you have in the Unix platform, where you can pipe different programs to achieve what you like. So what we see here is the way this is built is you have small programs that do a single responsibility, that have one and only one responsibility. But the beauty of it is you can chain them. You can chain them together to go get me a list of processes, and then chain that into, find me something that's of this name. Or you can go get me all the list of files on this, all the open files, and then start paging them. Or you can, move them around. And that's obviously a desirable characteristic. So microservices sets that pretty clear out front, that this is a very desirable characteristic. We really love this single responsibility, composability thing, and we would really like to draw from that and understand how can we succeed. And the whole idea is that right now our applications are big monoliths where you try to deliver one thing, but it's got X dependencies coming in and it's got N responsibilities going out. The context blows out. You have a lot of cognitive overload, and hence things don't move as fast as we would like to, and hence the motivation to go, if we can build something like this, which is composable and pipeable, as in it can be composed, you can change things together, life would be a lot more easier, because then you're only tackling with one program that's only meant to do one thing. So if you look a bit closer, what lets you do this? The most important thing that lets you do this is, for piping, is the most basic concept, is what's going out from here needs to match what's coming in, so then hence you can pipe it. And that's what's happening here, really. The output of a program matches the input of another program. So the magic really is, so the way I look at it is, you're designing programs that take input from at least one of your other programs. That's the only way you can pipe them together. Because if you write programs that take input that doesn't align to anyone's output, then you can't really pipe it. You have to have someone do it manually for you. So, right, so I just try to elaborate that by, so I'm referring to these things as programs. That's on purpose, because I don't want to allude to a service or distribution or anything. I'm using the word program more to say it's something that's built to do one thing well. You could imagine it as, from the .NET space, a DLL or a package. So these cogs are programs, right? You've got 4 of these, and you can see they do one thing well. So it all takes one input and produces an output. And you can see the next cog really is built in a way that it knows that if you've given it that one, it produces something else, and so on and so forth. So I've kind of replicated that design philosophy and said that now you have programs that kind of take an input that really are an output of something else. When you have that, what you can do is, you can put a pipe exactly like what we see there, and there comes output. On the other end of the pipe, if you put one of the cogs that really listens to the same output, you can go, yep, I'll pipe that into you, and out comes something else. If we put anything else on the other end of the pipe, which is happy to accept the same output as its input, there goes one more connection, and eventually it overflows. I've deliberately put the last one in there to show it. That's the composability part, where you could have either entered through the red cog or through the green cog. Really, they both prepare the same. They both give the same output, and they can be coupled. They can pipe into the one at the other end. But notice the red one and the green one are taking some inputs that are not really used by anyone else. Chances are they're participating at the boundary, because they can't be chained in to anything else in the process, so they will participate at the boundary, where probably an end user will need to come in and give them, or give it, that output. Did that stop? Right, that's better. Okay, so we can see exactly how that's achieved there. It's pretty simple. But let's now look at, let's compare to programs we commonly see. We have things like reserve stock. That's one thing. We have things like a charge card. That's exactly one thing. Now, if you look at their how they're designed, now that's the giveaway. They're saying, if you give me like an order stock or something, I'm happy to reserve it. If you give me some order payment details, I'm happy to charge it, right? Now, this is not necessarily the output of anything else. It's more, this is what I need to fulfill this operation, right? That's the interface it's designing there. Now, what you get as a result of that is you have place order that obviously now needs to call into reserve stock and charge card. That looks like a collaborator, which is a valid thing, right? What if the user wanted to do both things on one click, right? But let's ask ourselves, does the user want, do we allow our users to reserve stock whenever they want? Chances are no. Chances are you really want to only reserve stock when you have a valid order. Yeah. Chances are you only want to reserve stock when you have a valid order. So really, that's what's happening. Place order is not really a collaborator. Its actual responsibility is to receive the order from the user. So it's participating at the boundary. It's validating the order, and that's its core responsibility, to take that order in from the user. But because our downstream programs are not built to consume anything from upstream, place order is now forced into calling 1 and 2, because how else would they be invoked? You can't really, you can't really pipe them. What you have here is orchestration. It's localized. And orchestration is kind of prevalent with most of the systems I see, and I'm sure it's not new to you. And it's a byproduct of interfaces when you design them in this way. And what it gives is programs with a lot of responsibilities, exactly like place order. It's got 3 responsibilities. Core responsibility, receive order, buy products, reserve stock, and charge card. And possibly, you following the same mandate, you'll also have reserve stock and charge card probably do something else. Because chances are, if anything else needed to happen downstream, you would have the same cause and effect where those downstream interfaces can't just happen. You have to call into them. Now, how can we fix this? We just saw a while back how the Unix way is, how things can be piped, and how things can be composable, and how things do only one responsibility. So let's start again and go place order. You're supposed to receive an order. You fulfill your core responsibility, which is do whatever you need to do to validate the order, and you produce an output, which is order received, your core responsibility. Now, if we design our program reserve stock to say, I'm happy to consume that output, right, which is order received, and then I will, do whatever I need to reserve stock, and then I'll produce another output called stock reserved. And then if you move forward in the same way and go, I have a charge card, that program I want to design it specifically to consume stock reserved, and then do whatever you had to do, and then publish payment received. This looks a little bit closer on the surface to what we saw earlier with the Unix programs, where like, how does that happen? It's like you didn't say that right. Do it again. Yeah. So that looks a bit closer to the programs we saw earlier. What? Is it? Oh, sure. I'll turn that one off. Right. So again, so that looks a bit closer to the programs we had earlier with our Unix stuff, but now really they're not connected the way they're supposed to be. Unix connects them by throwing in a pipe, so why not? Let's throw an event pipeline in between. Now, like I said, I've called them programs for a reason, so I'm not implying any distribution here. What I'm really implying is how they're designed and what their APIs look like, and how the collaboration or the lack of collaboration is happening here. So you have an event pipeline, and exactly the Unix way, when you put them all together and order received is pushed on the pipeline can go. The pipeline can go, is anyone on the other end willing to consume order received? Oh yes, there is. I've got reserve stock. If you pass it on to that one, reserve stock then gives you back stock reserved. Then the pipeline can go, is anyone else plugged in on my other end that wants to consume stock reserved? And you've got charge card, and that happens that way. So if it's a simple design shift, but if you do things like this, now you get this composable single responsibility units. Somewhat, I think now that draws a bit closer to the inspiration from Unix, where we design things to do one and only one thing. Now, I've obviously said, so, okay, I just showed the interfaces. So now the interface, it's changed. Now it's explicitly saying, I'm actually taking in order received, as opposed to, this is what I need to, it's got more context now. Because it's not something that's reserve stock is not something that's participating at, hello?
Turned it down.
I've just turned it down a bit
Too much feedback.
to maybe reduce the feedback. So hopefully,
Yeah, sure. Yeah, so reserve stock, chances are it's not participating at the boundary. So really, by design, it cannot be invoked anytime. It can only really be invoked when an order has been received. So that's even a better design now, because now it's explicitly declaring the context in which it can operate. We're saying it's only when I can only consume an order received. I'm not willing to just take in some stock and reserve it for you, for anyone who can call me. So now you've explicitly captured the context in which it can run, and the same for charge card. Right. So now, as you can see, prefer choreography or orchestration. That's one of the core. If you read through Martin Fowler's article, that's one of the core kind of tenets of microservices, if I can say that, which is you prefer choreography or orchestration. Now, why choreography, and why is this better? Simply for the fact that the participating programs are rich in context, and there's no if you had to do, I'll actually demonstrate a simple example. Let's say the business tomorrow comes along and goes, hey, when we receive orders, really, by the time you process this whole thing, the user might go away or something might crash. We really want to send them an email as soon as we have received, as soon as we have accepted their input and go, that's valid. We want to give them an email. Now, in the traditional systems, you have to change someone to take on that new responsibility, and with that comes all the cognitive load of, have you tested this correctly, and have you done it at the right time, and what else is the side effect? With systems like these, because they're just built to do one thing and they have no context of anything else, they're just fulfilling their core responsibility, you can very easily just go, okay, let's build another program that's meant to take in order received. And you plug it into the pipeline. What happens now is when you go place order, 2 people are participating into received. Stock chugs along and does reserve stock as it's meant to, and order receive and send email on the other end. We'll also take order receive and send the email. This is open and close principle there for you, because without modifying any code, you could just add in another program and have it participate into in the flow. And that's why it's called choreography, because how things behave is kind of ordained beforehand. Components declare beforehand, programs declare beforehand that this is the event I'm listening to and this is how I'm going to behave. There's no one live trying to orchestrate to go, you go first, no, hang on, then next, but hang on. There's no toing and froing based on what happens in a live environment. It's all preset. So I guess at this point, my goal was to explain that, albeit a simplistic example, but when you take this approach and you build programs in this way, you would have in a very large manner tackle complexity in a way that it's all segregated and in single responsibilities. And if you really pay attention, you can notice that these programs, even though they're running in process right now, they can be packages. They can be developed by different teams. They can be their own repositories, right? If you're on the JVM, you have a number of languages you can write them in. Same for the CLR, you can do them in more than one language. You just don't have distribution just yet. And that's deliberate on my part, because I wanted to show that it's not so much distribution, you have to get this right first. Get the main goal of composability, of single responsibility, of modular components correct. And distribution sometimes gets in the way, because you have to now tackle a lot of different things. So it's more the design that should be our goal, and understand how we can design components to be like this. So when you hit this with your application, sure, no one's denying the fact there's a database hiding there somewhere, and chances are everyone's coupled to that database, but at least in your business layer, everything is modular, everything is in their own repositories, and you have this rich composition happening. Obviously, because it's all in process, the most obvious question would be, what's the load story? You're not adding distribution here. What is the load story? What happens when, given now we can iterate quickly and we can add better value, you get more foot traffic, how do you handle load? So the user calls into the first program, which is receive order. What's happening behind the scenes is a lot of other programs are participating into that, events flying here and there. They're all, what? Right. So, yeah. Yeah, so you have these programs all participating and doing the eventing, but from the user's perspective, all of that is in the one process. So which means that till the last one hits, it's all running, they're probably still waiting there. And as you have more and more users, that's obviously less than ideal there. But really from what we could do as a very easy win here is our place order itself, when it takes in an order and it validates, that's all it needed from the user. What happens from there on is really very little to what they can do there. So you can very easily just take that event, proxy it out, serialize it out of process, take it back in a way that your application domain really is not aware of it, and now where you had one, you have two processes. So the user, now if you follow the flow, the user basically calls place order, it goes into, the event is fired, but it gets proxied out into some sort of database or queue or whatever you have there, and the user returns at that point. And then it plays back into another process where the rest of your whole application is running. So now you've got that response time you wanted for the user, where he's returning quickly, and the rest of the process still chugs along. But obviously, you can't escape from the fact that even with those two processes, all your queries and all your commands, everything is going to that one database, which is a big monolithic database. Chances are you've got 15 queries coming out of the order table and 70 queries coming out of the products table. So that's still your chief bottleneck. Now the easiest way that I've found I can handle that, albeit if the technology allows for it, is master-master replication. SQL Server will charge you an arm and a leg for it, but it's now available in SQL Server too, for the .NET folks. So you do master-master replication, and then you shard, divide and conquer your messages into. So you take the process that's happening in the back, and you shard it. So obviously, why sharding and not why load balancing is because when you shard by, say, SKU, in effect what you're covering yourself for is all the counts, all the orders for, let's say, an iPhone will come to one database, and all the orders for a Samsung will go to another database, which means your counts, you're not dependent for the replication to be up to date and by the second for your counts to be aligned. If you just load balance them, your orders will just round robin or whatever go across. The counts will need to be constantly synced, and if they go out by even a second or two, depending on your domain, you're probably going to oversell. So if you shard by the SKUs, then your counts are still, all your counts for that SKU, chances are still in there. You'll still have a problem if iPhone alone gets so many orders that you go down, but I guess that's in a good, you're in a very good position if that's the case, considering Apple went down. So I guess at this point, the idea was, what I wanted to convey was, you've come this far, you've got the modularity happening at the domain level, right, where you have the composition, you have the eventing. So you have torn apart code that right. So yeah. So you've come this far. You've got before where you had these classes that were doing too many things and taking too many dependencies, and that was just by design. Now when you open your domain, you have these classes that are doing. You have these programs, these packages that are doing one thing. They're probably all getting composed. You have different repositories depending on your how you've segregated your domains and your teams. They all get deployed, and with minimal distribution, you have distribution to the point that you have two processes with the users coming through one, and then you have another one. These two are really just load balancing. With minimal distribution, you have almost taken account of most of the load that will come your way. We still haven't gone the full kind of distributed, how do I do n different things kind of way. You've just tackled it to this point, and I think this is key to get all these things correct before you really try to go out and make this into 17 more applications. It is key to understand how you get this. If you fail well before this, and if you find it's too hard to build things which can just compose and click, then chances are distributing it is just going to make it worse for you. Because the only thing that's worse than an application that, just where all the components are connected like this, is an application where they're connected like that, except there's a network and there's latency thrown in for fun. So then you deal with things like, this thing needs 17 other network calls to succeed. What happens if one of them fails? What's my compensation strategy? What's this? And you just, and now you have the deployment pain of how do I deploy 17 applications? Because microservices says you should never have that order. It's all decoupled. But because you didn't change your design, chances are you have a dependency on which order you deploy now. So it's n times the pain. So I personally, this is exactly what the way I approach it at SchoolCon, is where I, on purpose, did eventing in memory this way so that the team really embraces how rich eventing is and how can you write these decoupled components, and it clicks. And they understand, how do you write components that do one thing, and they just push an output to go, this is done, and then what else needs to click into that. From here on, obviously, if you look at an overview of our application, what we have is something like this, where you have all these different small programs. They're composed of use cases that encapsulate behavior, which is a big win. Compared to all the many dependencies that we were taking before, but that's not going away anywhere. Coupled at the database schema, and the database schema is obviously as bad as our resource. Now I've deliberately taken this approach where I've tackled it at the domain first, and not so much at the database. The traditional, or for the lack of a better word, conventional wisdom here. What we do is when we design an application, we start database up, and then often when we refactor them. So often when we refactor them, we kind of look at the database first and go, this is so painful. Why are 15 things talking to my, to this custom table? They shouldn't. And as a knee-jerk reaction, what we do is, don't talk to my table. I'll give you this interface. Talk to that. And then no, don't even talk to that interface. I'll make that interface into an API. Talk to that, right? You're still dependent on the same table. You're still making those 17 queries. The difference is now you're making them across the network, right? So the dependency hasn't gone away. So just simply taking what's consuming your database and pushing it out and exposing it over REST is, in clear words, exposing your database over REST, right? I'm not sure if that's a plan to save the world, but it takes in a lot of pain, trust me. So the approach that I've taken here is understand your domain, right? Get your modularity correct first. Your use case is correct first, because data really goes with behavior. Now when you have your behavior outlined correctly, now it's easy to go, what does managed stock need? I can see it talks to this table, true, it talks to this, so this is your tables, right? You've got product, you've got customer, you've got orders. What's chief here is data is modeled around nouns, right? What you learn in uni, really. And nouns are often overloaded in this case because it means different things in different use cases. For example, what does a order mean for the program that's billing? Does it care about the shipping address? As in, what does order mean to the program that's reserving stock? Does it care about the credit card details on the order? Does it care about the name of the person on the order, the one who's reserving stock? So yet they're all going to the order table. So what we should be doing instead is model data around behavior that needs to operate over its life. It's a mouthful. What I mean by that is, can we populate, for example, shipping details with stale profile data? Right? Imagine that. So when the customer tries to maybe change his profile and then come back later, even though we don't have distribution here, I want you to think about this problem because really the aim is eventually he might distribute. So to understand the nature of data, when the customer changes their profile and then probably goes ahead and tries to place an order, when they come to the shipping page, you've populated their profile. If that's out of date, chances are that they're not going to be very happy because they just went, I just changed my name or changed my email and now you're still not picking it up. So shipping is not probably the one who updated those details, but it's dependent on it. It needs them whenever it's enacted. It needs live data. So really put data together with model data around behavior that needs to operate over live. And so what I'm getting with that is there's two core things. So this is, the slides from here is really about, we're here. We've kind of solved what we did at the domain level. Now we really need to solve this monolith in the database and understand how do we, how do we not have 15 queries come to the order? And we have our programs that give us the context in which they run, but now you have to understand which one's doing a query, which one's, as in when you're querying this, do you need it to be live? Can you just wait if it comes from somebody else afterwards? And the approach I take for that is I take the program, I go, what are the things that you need? For example, charge card. What is the live information that you need? You need credit card details. Because if the customer changed the billing details a second ago, you should pick that up. So you need credit card details. What else do you need? You probably need to know if you can bill the customer or not. So a second or 5 seconds before you go and bill them, if customer service happens to log in and go, not approving his order, really you shouldn't be approving his order. So the reason why I'm giving this example is charge card is not really responsible for that information, yet it depends on it. So that's why I'm saying put data together where obviously the data it creates, so the transaction ID which it will create will be in that schema. The outcome from the gateway will be in that schema. But other live information goes into that schema. And then obviously similar for ship order. So the pattern is look at your programs because you've got them well defined. Understand what live information they depend on. Extrapolate that and make that into a schema. Still in the same database, but make it into a known schema. Lock it down, right? Have that come out into views, schema-bound views, if you may say. And then whoever else needs that, like maybe when you send emails, when you generate invoices, they need a lot of information, right? They can come from those views. So now you still have coupling, but you have coupling against a certain contract, not against your design. As in now the emails was trying to pull in everything is really looking at a view, not looking at the way tables are structured inside charge card or inside ship order. So when you make changes to anything, to the table structure inside charge card, sure, things will break. But now you have an explicit contract that protects you, so you can see these are the views that are broken. You can change those views. It's an easy way to start decoupling the dependencies that come directly to your table, and in a way define implicitly or explicitly that anybody else, you come to read-only views. You don't get to modify that information. That's what you get. And obviously, the information that you write gets replicated in there. So what's happening here is charge card, if it needs anything else from somebody else that it doesn't own, queries, its own information is in there. Similar for ship order. Things like, I can't think now. Ship order would need information where, okay. Record order payment method. This is what I was alluding to before. Record order payment method is the one that's creating, is the one that's capturing the credit card details and storing them there. Charge card is using them live. Now, and report fraud, which I was mentioning earlier, is when customer service comes in and says, that guy's a fraud, we don't want to bill him, he'll charge us back. You want to immediately store that there. Now, from a conventional perspective, when you look at this design, and when you come from the outside, you go, customer service is trying to mark a customer as fraud. That should probably go against the customer table. And then you might go record order payment. That's against the order. We'll put it there. Now what you've done is when charge card is going to come in and try to bill, he will have to make queries out to these other people, to these other tables. So store data not from where it's modified, or not from where it's displayed. Store data with with the entity that uses it live. So even though you were reporting fraud from a customer screen, even though you were placing order from a checkout screen, or it looks like it belongs against an order, bring the context down to, bring it closer to where it's used. And if you follow this, what you'll find is part of that order, like payment and whatnot, got into billing. Part of the order, which is like shipping details and whatnot, went into shipping, right? And then your warehouse information, like your stock, like what are the order lines that you've placed and how much quantity and whatnot, went into reserve stock. So where's the order? Chances are it's a view, because all your services have picked apart, have now got the pieces that they need, and only the pieces that they need to fulfill their functionality. So the order thing that we are so used to create, it's almost the first thing even I have created in most of the systems. The first thing you come in is you go, oh, we need an order service, we need an order table. It's not there. It's really a view that comes from all these different services. Similar for status. Now you don't have people fighting over the order status. Who owns order status? Which program is going to modify order status? It's not there because order status does not have context. Here you have context. Charge card is going to say, did that bill, as in payment received or payment declined? Ship is going to say, did that ship or not? Reserve stock is going to say, has it been reserved or it's not been reserved? You can collect all that information up and display it in your order view to the user and say, this is where you're at. These are the functions that we have done, without explicitly having an order table there. So, because now you've discovered this, hey, I've got 3 programs, and together they bring this information that they use amongst themselves live. They together form your bounded context. That's to me the definition of, okay, that's the data that needs to be encapsulated, and these are the programs that participate with that data in modifying it and and using it live. They become your bounded context. And same at the bottom over here with ship order and record order shipping. That becomes kind of your shipping context, and whatever else participates in that live information comes to there. And anything else that they don't directly modify or need live comes via views. So this is setting you up to understand the different boundaries that you need to respect inside your database with your design, really. It's kind of doing the same thing we did with what we did in the application, where we kind of picked apart things, said, you take one thing in and you publish one thing out. At the database level, we're kind of saying, what exactly do these programs need? And you follow the trail and you break them apart. And then you look at all the different programs that come together and operate on that data, and that forms your bounded context. And what you'll find once you do this is really your programs and your data are defined by your use cases and your behavior. It could very well be that one of the programs from here is deployed, so I think that's on the next screen, I'll get to that. So a bounded context is a logical grouping of data and programs that operate on that data, like that. This is a logical grouping, where you go, that's billing, it's got all these different programs, it's got its own schema. Likewise, you've got a few of the bounded contexts. But really when you go distribution and when you go endpoints, what you're looking at is something like that. It's homogeneous, where these endpoints can really have more than one program from this different bounded context or service from SOA parlance deployed there. So the point I'm trying to make is endpoints and services, it's not a one-on-one mapping. Your services really are your bags of data and behavior that go together, a logical definition, as in your repository or whatnot. Your endpoints are more defined by the commits that are required within a business transaction. So really, before this slide, if the business was really happy to where you came, where you sharded the whole thing and it was all fine, if they had no more load requirements, you had all the rich capabilities that come with all the work you've done without any of the distribution added to the mix. The only time you throw in more distribution is when the business goes, no, really, when we reserve stock, we want that to happen in its own transaction, isolated. And after we've reserved stock, billing could take a while. We don't want reserve stock and billing to just happen the same thing, because chances like one fails, it pull the other one back. So when the business makes that call and says, when stock's reserved, it's reserved. The fact that billing failed, you can retry it. Right? You call the customer, you chase it up, it's an out-of-process thing. When the business makes that call and says, make that out-of-process, that's when you go, that's an endpoint. It needs to go out-of-process. and then based on whatever they want in that endpoint, you pick and choose the programs you want, and you deploy. And because your primary construct, what's the better word? The glue between all these services is kind of the pipeline, the mediator pattern. You're good. You can do that. You don't have to always go to do that endpoint. You don't have to always go out and come in, or you don't have to go through APIs and whatnot. You don't have to do all this distribution. They're all there. If you throw them together, they'll work. Because you already got that right before you came all this far. So now you can get into the distribution you want, but now it's more in the context of what should my commits be, what are my SLAs. If emails, chances are it's really slowing you down. If it was all in process, emails would really slow everything else down. The business would go, we don't want to throw all that power at that, at emailing, put it behind a cheap box or whatever. Let it chug along. Emails can go 2 hours later on a busy day. Let everything else go faster. There the business is telling you we want different SLAs. Sure, at that point, create a new endpoint and then drag whatever programs you want to fulfill that commit and put them in there, and they will behave, even though they really come from different bounded contexts. And obviously many programs from different bounded contexts can operate within an endpoint. So that's the long and short of how I have approached this with Scoopon and at IBSA. This is not, a lot of this is from Uri Dahan, his version of SOA, of how he defines. So for me, this journey really started when 3-4 years ago when I went to his advanced distributed design course. So it was easy for me to really go into a 5-day course, have my mind bended, and then come in and start applying these things and see how they work. Hence this. But the goal of really the talk was to make you think that if you want to do microservices, the whole idea is you have to break this complexity apart, tackle it at the domain first, get all that right, get all your boundaries correct, get your context captured properly, get the rich composition that you really need, and then come to this point. Chances are, when you eventually, if the business so demands and you come here, you will not and you should not see a scenario where you try to deploy one thing and you go, what should go before that? Or what should go after that? Because all these small components are really doing one thing without the knowledge of what happens next and what happens first. So they can all behave well together. Obviously there's a lot, it's not as simple as I'm making it out to be. There's a lot more that goes in it, but there's only so much I can get into one talk. So I really wanted this talk to be about this approach that you need to take. And I honestly think for most teams, you can come to if you've come here, you've really solved the problem of your domain, trying to really, the database aside. You've done well. You're trying to understand most of the challenges with how to decouple things. And then this is challenging enough. This is, this takes practice to understand. You will always, you need to iterate a lot more over this, because trying to understand how data is aligned with behavior always takes a lot longer. So you can leave this almost like the last lap and get all the richness in your domain correct first, and then you can move on to everything else. So that's really the long and short of it. Well done. Thank you.
Take any questions?
Yeah, sure.
Can you give another example of sharding? So what does sharding mean in the context of microservices?
Sharding really is not, I'm not sure when it's the context of microservices. Sharding is more about, think of it as load balancing, where when you load balance, you have no control over how the request. So if you create if you create two copies of your application, which go to something like this, right? You create two copies with two databases. If you load balance them, then you have no control over which order lands where, right? They will land wherever they want, right? So let's say on a busy day, if you had 5,000 iPhone orders come through, chances are 300 will be, or 3,000 will be here and 2,000 will be there, right? what sharding gives you is you can say, so I'm talking, when I said sharding, I meant both. Shard at, shard the databases and shard it at the request level. So when requests come in, almost go, right. Yeah, so when requests come in, when you separate at the database level, you almost want to go, you know, all your iPhone requests should really go to this application with this database, and all your you know, other SKU requests should go there. And the reason for doing that, like I've said earlier, is so that when the databases start collating counts, all those counts for that SKU are in one place. Because when you do master-master replication, the biggest pain point is data is being written in both places. It needs to constantly be in sync, right? When you rely on something as significant as a count, which if it's out by you the slightest amount, you'll oversell. What you're then relying on is when orders for the same product come to both, you're relying on the sync to be almost live all the time. And whenever you have network in between, things will always go wrong. You'll always have, on a busy day, chances where you know, something gets missed, something gets skipped, and now you have to understand, you know, how do I marry that up? So it's a lot, when you shard properly, it's a lot easier to go, you know, that all these orders are over here and all these orders are there, and there's no aggregation that's going wrong. Information is either here or there. So I find that a lot easier to deal with than having to understand my counts are out because something just dropped in that replication. That's a very bad situation to be in. There'll be panic everywhere because, you know, when your counts are out, then you're going to take more orders. Did I answer your question? So yeah, it's really more in the context of, you know, your requests and whatnot. You know, microservices is. So to me, really, microservices. The moment I hear microservices, the question I think is, have you done your composition? Have you done your single responsibility properly? You know, if you're going to tell me we are microservices because, you know, we have 17 endpoints, but they're talking in the exact same fashion, I'm like, that's not new. You know, I mean, Corbett tried to do the exact same thing with, you know, the only difference is if that's all that microservices is, if you make it out to be, then the only thing you've changed is you've flipped from Corbett to DCOM to SOAP to REST. But your designs are exactly the same, right? And if you do that, then, you know, and at least I look at it like that. When I read a lot of blog posts, people are all about, with my 17 different endpoints, how do I deploy this? How do I spin everything in how do I, you know, spin everything so that, you know, it's load balance and this, and we use this tool and that tool, and, you know, and what happens if the network fails, and then you have these blockers in between and circuit breakers, and it's all technology thrown at the problem because what they're trying to solve is I have 17 endpoints, how do I reduce the pain? That's fine, but, you know, can we solve the core problem, which is the complexity that comes with everything talking to everything else? Can you decouple that first by doing your eventing properly? Sorry.
So eventing properly, how does that work? I mean, like the event pipeline is sitting there. Is it like pub sub something, and is there like any kind of event complexity for certain topics and subscribers?
Yep. So with what DAC is in memory. So from the .NET space, all that's happening there is if you have, now I purposely showed I charge card, right? But if you have an interface that says I handle stock reserved, which is effectively, you know, charge card. On the other end, if you have an I handle order received, right? And then on the other end, when that guy says order received, it really has a, the pipeline is a mediator. It's.
I don't know, I understand that. But
yeah.
Like, you know, like
no, there are, because it's in memory, there's no topics and subscriptions. All that's happening is you're calling a mediator and saying, I want to say order received. The mediator on the other end is going to go, it's going to scan its, if you have an IOC container, it's going to scan its object registrations to go, is any object with this interface register that says that it handles order received. So I see I have 2 registrations for order received, I'll invoke both of them.
So that's a specific piece of .NET technology that you're referring to, the event pipeline like that? Or?
No, it's the mediator pattern. With, you know, so basically what
it's
happens?
Not physically separate.
It's not physically separate.
No,
it's
there's
all
no
in,
separate bus.
There's no bus.
In memory.
So
There's some function in the middle that would handle the coordination.
So continuing with that question, so what do you do if you need to separate them, if you need to deploy them to different boxes?
Yeah, so obviously the idea of doing this approach is you register the fact that this is how eventing works. you register the fact that when do things handle events, how do things, how do you do one thing and then two things happen off it. Once that registers, now you have to distribute it. Obviously, if you need to distribute it, then you got to almost change your in-memory mediator, or like I said earlier over here, the way I do it is, you can kind of almost, depending on your messages, right? So let's say you publish or receive, and now business says, whoever's listening of that can't be in process, it needs to be done outside. So you can attribute that message, or you can define that message in a way that when your mediator receives it, it goes, I'm not going to literally replay this to my other subscribers in memory. I'm going to time it off to a proxy, which is a bus, and that proxy could take it via RabbitMQ and take it on the other end, and then from there it again continues. So from a domain's perspective, it's no different. As in, if you would open all the different handlers, they don't know that things are going out and coming in via Rabbit or the bus or whatnot. They just go doing eventing.
So messaging is not the first class citizen. You always go through memory first.
Messaging is the first class citizen as a construct.
As a construct, yeah.
As a construct. So the idea is that, because the moment you talk messaging and eventing, that's exactly the question. People try to stumble on, do I need, do I need all this? Do I need Rabbit? What do I need? Do I need something else? Do I fan out? Do I this? Do I that? What are your guarantees? What are your rollbacks? So I almost want to go, no, let's not go so far. Let's first just understand how this whole construct of messaging and eventing and subscribers and whatnot works. And once all that registers to you, hopefully distribution comes as a logical, next step.
So I guess the physical nature of the transport is independent of the concept of having an eventing bus and an eventing pattern. Okay. I'm just conscious of the time, so if that's okay, we'll cut off the questions there. So we'll have a 5-minute break and we'll do some logistics, change over. It sounds like the microphone might have died. And we'll get ready for Beth's presentation.